So this is the second part of the lecture. Yesterday we talked about some evidence for dark matter. We know that they exist, but we haven't seen them yet. So we talked about some possible candidates, and in this lecture, I will discuss how to detect them. This is actually closer to what I do. The first lecture is necessary for motivation, but it involves many things that's beyond my expertise. But hopefully, I can show you more details in the how to detect them. Okay, so this is a picture showing where we are in Milky Way galaxy. So our sun moves around the galaxy at about some 200 or 300 kilometers per second. And our Earth moves around the sun. And so yesterday, we talked about this dark matter halo surrounding the Milky Way galaxy. So as we are moving through this halo, we experience this dark matter wind blowing towards us. And depends on the season, this wind may be stronger or weaker, depends on where we are, how we are moving in our solar system, right? You can see our solar system is forming an angle with respect to the galactic plane. And so you can imagine how this relative dark matter speed changes over the year. And this provides some handles on how we detect dark matter. Okay, so one of the main technique to search for dark matter is this direct detection method. So we try to look for the scattering between dark matter with the nucleus and electrons. So with the nucleus, we call it NR, short for nuclear recoil. So a dark matter collide with the nucleus, and the nucleus gains some energy, and we try to detect this little motion of the nucleus. At the same time, it's also possible that this dark matter would collide with an electron. So electron would gain some energy, and we try to look for the signals in our detector. Of course, there are other detection techniques. For example, this axion detection. So I mentioned yesterday. So axion may couple with photon, so they can convert into photon. And we try to look for the photon signal. And another possibility is that this dark matter is absorbed by an atom, much like the photoelectric effect. So the photon is gone and an electron is kicked out. So this is under the assumption that this dark photon is coupled with a real photon. Okay. So let's first look at the recoil kinematics. There's nothing more than the conservation of momentum and energy. So if you work out the two-body interaction equations, then you end up with this expression. So T is the final kinetic energy of the target nucleus, M2 here. And A is the ratio between the masses of the two particles, the target mass over the incoming particle mass. That is the mass of the dark matter. And then you have a scattering angle phi. So if you take a derivative with respect to A, you can find out that when the two masses are equal, you have a maximum recoil energy on the target nucleus. So I think you probably have the experience with the pull. The balls are of the same mass, and if it's a head-on collision, the incoming ball would stop, and all the kinetic energy is transferred to the other one. So that's how you gain the maximum energy transfer. Right. So here I have some exercises. I guess Blackboard is not so convenient. So I will just pose the question here. Maybe you can do some exercises later. So imagine you have a 100 GeV dark matter particle, and it moves at the speed of 1,000th of the speed of light. What is its kinetic energy? Since it's a low speed, we can just use 1/2 mv squared, right? And it's easy to get the kinetic energy. And if you consider the collision with an electron, how much kinetic energy the electron gains after the collision, and the scenario with, say, atomic nucleus with mass number 100, that is the mass that is very close to the incoming dark matter particle. So those are very simple exercises. I will just give the answer. So the kinetic energy of the dark matter is actually not that high, just the tens of keV. And if it hit on the electron, the recoil energy is tiny because we have a huge difference between the masses of the dark matter particle and the electron. But if you consider the nucleus, because the masses are comparable, you have a very large energy transfer. So you would look for some nuclear recoil of tens of keV in your detector for the dark matter of this mass. Okay. So with this kinematics solved, we can look at the event rate. So consider the dark matter flux, F. So this is due to that we're moving through the halo. This flux is the dark matter wind blowing in your face, right? And imagine the cross-section is sigma, and you have a detector that contains a lot of target nuclei with the number n. Then you can calculate the event rate. The event rate is just, I think the sigma is missing here, flux times cross-section times the number of target. And this flux can be further written as the number density of the dark matter particle times the speed it's moving, right? Sigma is not here. But the cross-section depends on the distributions of protons or neutrons inside the nucleus. So that's why if you write it in more detail, and if we try to write down in recoil energy bins how many events we expect, then we have this form factor here representing the structure of the nucleus. And then this F is the velocity distributions of dark matter. And very often just Maxwell Boltzmann distributions is used. We have a minimum velocity. So if we fix the recoil energy, you can imagine there is a minimum velocity that can cause this much recoil. And there is also maximum. So this is often taken as the escape velocity. So the dark matter cannot move too fast, otherwise it will move out of the galaxy. So there's an upper limit. Then you can compute the event rate. So here I just gave an example of what happens with the xenon nucleus. So you can see with the different dark matter masses, you expect different spectrum, right? With the heavier dark matter mass, you have a larger chance to have a larger energy recoil, right? This is, of course, assuming some cross-section. Yeah. Right. So to search for dark matter signal, there are a number of experimental challenges. The first one is the cosmic ray. So if you have a lot of cosmic rays, then they can generate isotopes in your detector. And more importantly, it can produce neutrons. Neutrons has no charge, and it can collide with the nucleus, providing very similar signals as a dark matter. So it's very dangerous. And for my own work, so I try to reduce the neutron background by vetoing them, or better estimate how many neutrons there are. And for this reason, we need deep underground laboratories. So this plot shows many of the large underground laboratories in the world. X-axis is the depth, and the y-axis is the muon flux. You can imagine as we go deeper, the muon flux becomes less. So I like this plot. So I worked on a few of them underground laboratories. For my PhD studies, I was working with this long baseline experiment. The FAR detector is located in the Sudan mine in Minnesota. And for my postdoc, I worked on neutrino stable beta decay. It's in the LNGS in Italy. And now I'm working with Panda X experiments in Junting lab. So I'm moving in the right direction, deeper and deeper, less and less background. Okay, so other background sources, cosmic ray can induce neutrons, but that's not the only source. Very importantly, this uranium fission, it can produce neutrons. It can actually produce multiple neutrons per fission, along with some gammas. So it's very dangerous, and no way to get rid of them. So since uranium, along with other long-lived isotopes, they formed even before the Earth is there. Their lifetime is comparable to the lifetime of the universe. So before the Earth is formed, those heavy elements, they can be produced by some violent astrophysical events, such as supernova. They produce those heavy elements, and they stay there since then because their lifetime is really long. So of course, this alpha-N reactions can also produce neutrons. We have a lot of alpha decays in those long-lived isotope decay chain, and if they hit on some nucleus, a neutron may be ejected. So this is also a neutron source. So in the materials, we have, so I'm listing here some long-lived isotopes. So their decay chains are quite dangerous. We have to build a detector with some material, and how to get very clean material is non-trivial, and it's difficult to have some material that has very low concentration of those uranium, thorium, or potassium. And what's more troublesome is that if you look at the decay chains, so there is a radon in all of those uranium and thorium decay chains. So they are dangerous because they can come out of materials. So if, say, a material contains uranium or thorium, so they decay, beta, alpha, they can never come out. So we don't worry too much, but this radon, they can come out of the material. So in the laboratory, in the walls, or on the ground, it's emanating radons constantly. And in our detector, there are pipes, they emit radons constantly. And this creates a big trouble. This I will come back to when I talk about the liquid xenon detectors. Okay, so, and then there is a neutrino background. So this background we can never shield or get rid of because neutrinos are very penetrating. So we call it irreducible background. So this is also the source of what we call neutrino floor. So on the Earth, we see neutrinos from various sources. From the sun, we have PP neutrinos, boron-8 neutrinos, those dashed lines. And then we have atmospheric neutrinos. So high energy particles hit on the atmosphere and produce a hadronic shower. And then neutrinos are part of the decaying products. And then there's a diffuse supernova. Those are from the supernova happened in the past. They have the energies of tens of MeV. So in this plot, this is actually a plot made specific for Junting lab. And so this blue part is what we call neutrino floor. X-axis is the different wind masses, and the y-axis is the cross-sections. As you can see, as our detector becomes sensitive enough, as we are pushing down the limit, eventually we see a lot of neutrinos. And at the high energy end, for the dark matter masses of tens of GeV, you can see the atmospheric neutrinos forms the dominant background, this red band here. And solar neutrinos, this red dot is actually from the boron 8 solar neutrinos. And I will come back to them later. Yeah, so you can see how solar neutrinos can create signals in our detector. This plot shows the nuclear recoil signal. And you can see it's this red line. This is a boron 8 neutrino, and it has a high energy, and it dominates in the nuclear recoil caused by solar neutrinos. It has the largest contribution. And if you look at electron recoil, PP neutrino plays a more important role. You can see there's at low energies, you can see it's way higher than the contributions of other solar neutrinos. Here I'm listing what we call as PP neutrino or boron 8 neutrinos. So they come from different reactions, so therefore they have different energies. Okay, before we start the experimental techniques, I will mention one more thing. So this is a so-called spin-independent and spin-dependent search. So this you see in the literatures very often. When we talk about spin-independent search, we meant the dark matter would interact with the nucleus coherently. That is, it would interact with the protons and neutrons in the nucleus together. The cross-section scales as A square. A is the mass number, the proton number plus neutron number. And so to search for spin-independent interactions, it's better to use heavy nuclei because of this A square relation. This is similar to neutrino coherent scattering. It scales with A square. And then there is a spin-dependent search. So we look for interactions between the dark matter and individual unpaired protons or neutrons. They have a spin 1/2, and so in some nucleus, we have say even number of proton number. For example, this is xenon 129. So it has a large abundance, 26%. So if you look at the Z number, it's 54, even number. But then neutron number is odd. So there is one unpaired neutron. So you can use this to search for spin-dependent interactions. More specifically, it's spin-dependent with the neutron. And then you can have, say, fluorine 19. It has odd number of proton number. So one can look for a dark matter spin-dependent with the proton interactions. So, but this is much weaker, and but the good thing is that it may help us to go below the neutrino floor that I mentioned. So this I will come back. Okay, so as for the detection techniques, there are many. In terms of the detector signals, we can have ionization, and we can have scintillation light. We can also have phonons. So a number of experiment names are listed here. So I will cover, I think, most of them. Okay, so this is a nice illustration of different detection techniques. We can use scintillators, we can use TPCs, we can use bolometers, or this is a gas TPC. So we will go through them slowly. So we will start with the scintillation detectors. I think many of you are undergrad. So I don't know if you have taken the particle detection lab. So this is a very common type of particle detector. So Scintillator are the materials where if you have a charged particle pass through, this particle can cause light emission in the scintillator. So put it simple way, so the molecules would be excited, and then as they de-excite, they produce light. So of course, the exact mechanism vary, and we have different types of scintillators. We can have crystal scintillators. We can have organic scintillators. It can be liquid, as used in Juno, mentioned by Liang Jian, or we can have plastic. So plastic ones are more expensive compared to liquid ones, but easier to handle. And we can also have noble liquid, such as liquid argon or so. If I compare those two, the crystal scintillators typically have a higher light yield. So the more light we can collect, the more information we know about the particle interaction. But the time response is usually slower. And the organic scintillators is the opposite. Light yield is lower, about 10,000 photons per MeV, but the time response is better. So this is an illustration. So we have a block of scintillators here. If you have a gamma coming in and interact with electrons or go through pair productions. So there are charged particles produced, and then they cause scintillation light in the scintillator. So then we use some photosensors to detect those light. The type can vary. In this picture, so I'm showing a PMT, a photomultiplier tube. So there's a front window coated with materials that is easy to have a photoelectric effect. So nowadays, the photomultiplier tubes typically have nearly 30% of quantum efficiency, meaning if you have 100 photons coming in, 30 of them can be converted to photoelectrons. But that's not enough. Single electrons is very difficult to see. Its charge is very small, and your electronics don't see it at all. It's just buried in the noise. So we have to amplify the signal. For this type of photomultiplier tube, you have a series of these metal plates. So then we can add potential difference between the neighboring plates. So for the first stage, we have a electric potential between the photocathode, where the photoelectric effect happens, with the first one plate. Those plates we call dynode. And so there's a potential, so electrons would accelerate toward the first dynode. And it can produce some secondary electrons. They spill out of the surface. And then we have potential between the first dynode and the second dynode. So those electrons would head toward the second dynode with some energy gained from the electric field. So then produce even more secondaries. And this process goes on. Typically, you have a 10 or 12 dynode. In the end, you can read out electrons on the order of 1 million. So this is what we call gain of your photodetectors. So with 1 million electrons, it's very easy to see them with your electronics or oscilloscopes. Of course, we're not limited to photomultiplier tubes. There are semiconductor detectors, for example, the silicon PM, and avalanche photodiode, and so on. So there are pros and cons, but I will not go into too much details on the photodetectors. So one very famous scintillator dark matter experiment is this DAMA experiment. So they use sodium iodine as the scintillator. So it's a crystal scintillator with light yield about 40,000 photons per MeV. So they put PMTs facing the scintillator, and you try to count the event rate. As I mentioned in the beginning, we are swimming in a sea of dark matter, and sometimes the wind is stronger, sometimes it's weaker, depends on which direction we're going in the solar system. So very interestingly, they detected those annual modulation signals, which agree very well with our expectations on this dark matter wind in our galaxy. So by eye, you can already see this is very obvious. So this is a long-lasting experiment. So this data span over 2 decades. You can see those sinusoidal waves. But like any other particle experiment, if you see something, it has to be confirmed by another experiment to be more, for the results to be more convincing. So experiments are built to investigate whether this is real. Here I'm only showing the two experiments which released the data very recently. They released the 6 years of data. One is called INES in Spain, and the other one is COSIGN in Korea. So I think, so this is what their detector looks like. It's just a sodium iodine scintillator block with the 2 PMTs facing the crystal. The setup is very similar. Then you have a lot of shieldings or veto detectors surrounding your main detector. And there's a paper last year combining the results from the 2 experiments. Blue is from one experiment, and red is from the other. By eye, you don't really see sinusoidal shapes. And from a more careful analysis, they don't see any annual modulations as Dama claimed. And also the Dama signal is also excluded by other experiments. So of course, people will continue to investigate. I think the experiments will continue to run. And so there are also new experiments in preparation. And eventually, we will have a significant amount of data to either refute or support Dama claim. Okay, now I'm switching to a different type of detector. They usually operate in a very low temperature, in tens of millikelvin. At this low temperature, you can actually sense the vibration of the crystal lattice, which we call phonons. I hope you learned in the solid state physics course. So if you have some vibration on the lattice, there are corresponding quanta of those vibrations, and we call them phonon. And so suppose you have some interactions happening in your detector, so the lattice start to vibrate, and the resulting quantity we can measure is the temperature. So the temperature would rise, and you can measure this temperature rise of your detector with some very sensitive temperature sensors. So for example, you can have this transition edge sensor or some semiconductor detector sensor to measure this rise of temperature. So the right plot just shows how this transition edge sensor works. So I guess you all know the superconductor. So if the temperature is below some critical temperature, it becomes superconductive. But if it's above that temperature, it's not superconductive. And so if you operate your detector just right at near the critical temperature, then your detector would be very sensitive to the temperature change. So you can see this slope. The temperature changes a little bit, your conductivity changes a lot. So that's how you measure temperature in a very sensitive way. So left plot just shows the vibration of the lattice that I just mentioned. Okay, so very often those low temperature detectors is also a semiconductor detector. So I will describe a little bit. I think very likely you have learned about this. So suppose you have an electron, a free electron moving through space. Then the kinetic energy of the electron is the square of your momentum, right? As shown in the left plot. But in a crystal because you have this periodic formation of atoms in the material. So those electrons would scatter off those lattice center. And because of this, you have some energies that you can never reach. So this is what we call the band gap. It forms this band structure where some energies or some states are just simply forbidden. And so this is the band theory, which can explain the differences between the conductor or insulator or semiconductors. So this is illustrated here. So if you have a band and it's not fully filled, meaning there are still some states where electrons can occupy. And as you add in electric field, those electrons can gain energy and jump to those empty states. So they can flow. So therefore, you have a conductor. But if you have a band which is fully filled, and the band next to it is very far away, so you need a lot of energy to jump from one band to next. And if it's fully filled, then the electron cannot absorb energy from the electric field because there's no states for them to jump to. And so they simply don't move, even though there is an electric field. So the semiconductor is somewhere in between. The band is fully filled, but it's possible for them to jump to the next band, which is empty, with the small excitations, either from thermal or some particle deposit energy in a solid. So this is what we call semiconductor. And so with this property, so when there is some energy deposition, so electrons would jump to the empty band, and so there is a free electron forming. They can move in the electric field. At the same time, it leaves a hole behind. This hole is not a real particle. It's a pseudo particle with opposite charge. They can also drift in an electric field. So the signals of your detector are those electron-hole pairs. So that's how we use a semiconductor for particle detection. Okay, let's come to some real examples. So I'm listing 3 experiments here. They are all cryogenic experiments. So their detectors operate in tens of millikelvin. And so they are good for detect sub-GeV dark matter. Supercity and MS, they use germanium or silicon. The detector is actually quite large. It's macroscopic. It's about 10 centimeter disk with a centimeter thickness. And so they can detect phonons, as I mentioned earlier, and they can also detect electron-hole pairs. So phonons and ionization signals are the main signals of their detector. So we also have this cryocell. They use smaller germanium detectors. They detect phonons, but they're very sensitive to the electron-hole pair. Even a single electron-hole pair, they can see. So that's their advantage. And then you have this crest. They use different materials. So this one, I hope you can recognize. This is a sapphire for jewelry material. And so light can propagate. So it's their signal is phonon plus light signals. They are also very small, and with this 20-some grams, they can reach a threshold of tens of eV. So this is quite impressive. So here I want to mention that in all the detectors of these types, there is a low energy access. So nobody knows where they come from. You would guess they come from dark matter, but those access vary in terms of rate and shape among different experiments. So unlikely they are dark matter signals. So people are still looking for the cause. Okay, CCDs can also be used as particle detectors. So this, yeah, so I guess in your phone, you have this photosensor array. Very likely it's a CMOS. CCD is I guess it's an older type of this semiconductor pixel array, but it's still in use because it has a very low noise. The reason is that you have those semiconductor arrays, very small, maybe 10 micrometer. So there are a lot of them, maybe thousands of them placed in an array. But there's only one readout. So when you read out the charges on the CCD pixels, so you read them row by row, or you finish one row and you move to next row. So you only have one readout component. So this can reduce some variations in the readout, unlike the CMOS in your phone. CMOS in your phone, every pixel has a readout, but then your readout may have some variations. So this creates extra noise. So that's why people still like CCD. And what's made them possible for dark matter detection is this escaper CCD technology. So when you read out charges in a pixel, you read it multiple times, non-destructively. This is good because then you can average out the electronic noise. And so then this very effectively can reduce the noise of your measurement. And so because of this escaper CCD, we can use them for dark matter. But the disadvantage is that it's very slow. You read multiple times and not as fast as one-time readout. So here I'm listing two examples. DAMIC, they are located in Snow Lab. They use a few pieces of this 4K by 4K pixel array. It's very light, just also on the gram scale. And Sensei at Fermilab with a very shallow overburden. It's also a pixel array, and with you can see the pixel size is 15 micrometer, and thickness is a few hundred micrometer. It's also on the gram scale. And this you can already see they can place a very good limit on a very small mass dark matter. And yeah, to be more sensitive, then you have to increase the mass. So the future, this is the next generation proposal, I guess 10 kilogram scale. You can see now we are at a gram or tens of gram. Now there's a 3 orders of magnitude jump to the next generation. Okay, so next type of detector is sort of old technology, this propulsion counters. So basically you detect ionization in gas with some electrode. So here I'm giving one example. It's called NEWS-G. It's a spherical detector with the anode in the middle. So if you have ionization happens in the detector, then the electrons can drift towards the anode. And as they approach the anode, the field is stronger. So there is some amplification happening. And so one primary electrons can become multiple electrons. And so then this way you can see single primary electron signal in the detector. Right, so you can see they can use different materials. And they already placing quite good limits on the low mass range. Yeah, so the detector is only 1.4 meters in diameter. It's not very large. It's a small detector. So initially they were taking data in LSM in France, and then they moved it to Snow Lab. With a very small exposure, you can see a very good result. And of course, there are larger detectors in preparation for different underground labs. This is a dark sphere sensitivity plot. Okay, now I'm switching to Nobel liquid. This is we're getting closer and closer to what I actually do. This is a periodic table, and you can see the last column is what we call noble gas elements. So those are very good because those are they don't form complicated molecules, a single atom, and some of them are very available. For example, argon is very cheap. If you work in the lab, argon, it's you use them maybe to dry or set up. It's very cheap. The density 1.4 gram, and so this makes it a very good target and has a very good properties, which I will mention in a moment. Xenon is more expensive, but still annual production is about 100 tons. This is more than we can dream of for a dark matter detector. Right. Okay, let's look at the liquid argon first. So liquid argon is a scintillator. If you have a charged particle pass through, it produces light. And the process is maybe more complicated, but the light comes from this excited argon, say, molecule, dimer, I think is the right name. When they de-excite, they emit light. And there are two modes for this. So one is called singlet, and the other is called triplet. I think this is related to quantum mechanics. And they have very different timing profiles. So different processes. One happens very fast, time goes out in a nanosecond scale. But the other one is very slow in a microsecond scale. And earlier I mentioned there are two channels. You can look for recoil on electrons, or you can look for recoils of nuclei. And for electron recoil, this triplet component is very prominent. But for nuclear recoil, this triplet component is much smaller. So this provides a very good way to do discrimination between the electron recoil and the nuclear recoil. Because electron recoil, there's so many backgrounds. If you have a gamma, you have a Compton scattering, right? It kicks out an electron, that's electron recoil. If you have a beta decay, that's also electron recoil-like event, right? But if we're looking for WIMPs, and if we look for the WIMP colliding with the nucleus, then you are looking for nuclear recoil. So if you can do the particle identification with the pulse shapes, one has a longer tail, one has a less longer tail, then you can reject background significantly. That's the good thing about liquid argon. So here I'm giving one example. So this is a deep 3600 experiment. It's operating in a snow lab. The detector structure is very simple. You have an acrylic sphere, much like Liang Jian mentioned about Juno detector, but this is much smaller, only 3.6 ton liquid argon contained within. So you see the radius is only 85 centimeters. And then you have a lot of photomultiplier tubes looking at this sphere. So if something happens inside the detector, it would produce light signals, and you read them, and you can look at the pulse shape to see whether it's electron recoil or nuclear recoil. Then you can use this to look for dark matter. Very interesting design is that between the sphere and the PMTs, there's a light guide so that PMTs can stay at a distance with respect to this container. So PMTs are radioactive, as we know. We don't want them to be too close. There's a different use of liquid argon. This is the so-called time projection chamber. So I will try to describe the principle briefly. This type of detector was invented in 1970s. So was by David Nygren. I think many of you know. So I think this was used in a collider experiment in SLAC or other places. And so the principle is this. You have a medium. Back then it's gas. And so when the charged particle passes through, it ionizes some electrons, and those electrons will drift along the electric field, and then they can be detected on one side. So you can have some electrodes to detect where the electrons arrive at this plane. So you can have this XY position measurement. At the same time, you can measure the drift time. So when the charged particle passes through, you have scintillation light that gives you a T0. And then you can compare it to the signals on this plane. The difference gives you the delta T. And you know how fast it drifts, then you know the Z position. And this is how TPC works. Of course, nowadays, we're not limited to gas. We can use liquid argon, as I just mentioned. So I give you one example, dark side 20K. This is an experiment in preparation, I guess, at LNGS. So they use 50 tons of liquid argon. You can see this is their time projection chamber. And they have a readout using silicon PMs on one side. So this is what we call dual phase TPC. I will explain it in a moment when we talk about liquid xenon detector. So those photosensor arrays can detect where the particles, where the electrons arrive, and also how much of it. And the Z position can be determined by the drift time. Right, very interestingly, they are using so-called underground argon. You know, if you have something on the Earth's surface, the cosmic rays keeps bombarding your material and would activate your material, meaning it produce a lot of isotopes, some short-lived, some long-lived. This we don't like because they are potential background sources. But if you use underground argon, so they are extracted from the underground, and then they are used underground. They have never been exposed much to the cosmic rays on the surface. So those are very quiet argon. You may also heard of this Roman lead. So those lead are sinked to the bottom of the sea during the Roman times. I guess when the ships sink, they stay under at the sea bottom for a few hundred years. They are very quiet, and they are very good building materials for a detector because you would expect much less radioactive background with them. So the underground argon is similar concept. Okay, so with this, they can expect to reach very good sensitivity with at a dark matter mass at GeV level. And of course, people are also imagining larger detectors with 400-ton liquid argon, and they can eventually reach the neutrino floor. Okay, now I'm switching to liquid xenon TPC. The operating principle is very similar. This is a GIF. You can see a dark matter comes in. It may interact with the nucleus, and it produces two signals. One is the scintillation, just like liquid argon. You have a scintillation light. But unfortunately, liquid xenon doesn't have this pulse-shape discrimination capability. Electron recoil or nuclear recoil, we don't see much difference on the scintillation light timing profile. But it has a very good advantage of doing the particle identification using what we call the S2 signal. So the scintillation light is what we call S1 signal. And after interaction, along with the scintillation light, the electrons would drift. Ionized electrons would drift in the electric field, and you eventually reach one side of the detector where you have a photosensor array. I think all the experiments are using photomultiplier tubes. But those photomultiplier tubes are not immersed in the liquid. They're actually a little bit above the liquid level. So there is a gas layer. And in this gas layer, we apply much stronger electric field. So when the electrons reaches the surface, they're pulled out by this very strong electric field and producing light signals. And so those light can be seen by those photomultiplier tubes. This is what we call the dual phase TPC. I guess I haven't told you what's a single phase. For the single phase, a typical configuration is that you have readout wires in X and Y. They're immersed in the liquid, so they can detect X and Y positions. But here you use photosensors to detect how much charge there are and what positions it reaches the top. So, right. So this the light caused by those electrons pulled out of the liquid. This is what we call S2. So it's very fortunate that for nuclear recoil, S2 is relatively smaller, but for electron recoil, S2 is larger. So we can use this ratio to do the electron recoil and the nuclear recoil discrimination. The reason why we want to do this discrimination is what I mentioned earlier, to reject background. Okay, so there are three main animals in this field. One is LZ, located in US, the Sanford Underground Research Facility. The middle one in LNGS in Italy, called Xena Wantan. And then there is a Panda X in the Jinping Underground Lab. So you can see the detectors look similar, but still there are some differences here and there, making them worthwhile for cross-checking. Right. Here I first present the LZ and Xena recent results. So left one is from Xena Entang, and the right one is from LZ, all very recent. So I guess I just explain a little bit how to read this kind of plot. So the x-axis is S1, the scintillation light. Y-axis is this S2, the ionization signal. And as I mentioned earlier, the ratio for electron recoil and nuclear recoil is different. So electron recoil would be somewhere at, for the electron recoil events would lie higher in this plot, and nuclear recoil would be lie lower, right? And then you have various other background. For example, the accidental background. And then you have this green one, which they call a surface background. And then you have a dark matter region. This is for specific mass of dark matter. So this contour. So this shaded red, for example, this is where the accidentals happens more often, and the green one is where the surface background happens more often, and this region is your dark matter region. So if you want to see signal, you would want a lot of events observed only in dark matter region, right? Well, I guess you don't see many in this contour, and so if you don't see things, as one of you asked yesterday, if you don't see things, that doesn't mean it doesn't exist. You can set a limit. So you can say the cross-section cannot be higher than this value. Otherwise, we would have seen it in our data taking period, right? So you can place a statement on how big this cross-section can be, right? Right. Based on this principle, you can draw lines. So y-axis is the cross-section, x-axis is the WIMP mass. Different masses have different limits based on your data. I think one of you asked about this yesterday. The right plot is from LZ, left plot is from Xena Entang. Okay, now I can give you more details about what we do. So this is the Panda X experiment. Right, so it's located in, sorry, there's some constant small noise. I don't know if it's bothering, but okay. let's see. Let me see if I can improve it. Okay. It's located in southwestern China. It's in the mountains. So this place is very interesting. There's a river flow by. You can see the path of this river. It goes around some high mountains, high peaks here, and continues on. So people want to use this to generate electricities with water flowing. But because of this detour, the momentum of the water has decreased significantly because of the friction. The water has to flow around. Then they found a way to improve the situation. So they want to dig a tunnel just directly connecting those 2 points so that you have less energy loss for the water flowing around. And then they can try to use those momentum to generate electricities. So that's why they have a tunnel here. So the underground lab is in the middle of this tunnel. And to the opening of each end, it's about 10 kilometers. It takes some 20 minutes to get there. And overburden, that's the best part, it's 2.4 kilometers. This is very deep compared to other underground labs. And so makes it very comparable to Snow Lab in terms of the cosmic ray flux. In fact, it's actually lower than Snow Lab. So then there are a lot of chambers built, and so PanX is in one of them. So the main detector is a liquid argon TPC, and it's immersed in water shielding. So there's a huge tank containing 1 kiloton of ultra pure water, and the TPC is not very large. It's just 1 person tall. It's sitting in the middle. Okay, some pictures. So this is the TPC. So there, you see the copper. They provide a uniform electric field in the TPC. So this is the photosensor array. This is the cryogenic system. So liquid xenon is about minus 100 degrees Celsius. So it has to be cold at the time of installation. And this is the electronics readout system. And this one is very special. This is a distillation tower. Because in the, I mentioned earlier, the radon is everywhere and it's dangerous. So it can come out of the material and go into your liquid xenon. So it's a background source. So this distillation tower is trying to remove radons in the liquid xenon. So it's circulation, continuous circulation. So the principle is that radon and xenon, they have different masses. So they have a different boiling point. So you can control the conditions such that so one of them can boil earlier. Lighter ones would boil, right? And so you can, by this way, you can get rid of them. Another thing we want to get rid of is krypton-85. This is also a radioactive isotope and also exists in liquid xenon. So we also try to use this technique to remove them. Okay, I guess this slide is the closest to what I work on. So this is a VITO system. I mentioned earlier, we have this ultra-pure water shielding. It's contained in this huge water tank, about 10 meters in diameter and 30 meters in height. So liquid xenon detector is sitting in the middle, just on a meter scale. And all the rest are ultra-pure water. So we built a Cherenkov detector by placing those PMTs, 8-inch PMTs, about 20 centimeters in diameter in water. So I think this I didn't mention before. So when charged particles pass through water, it can produce light. This is Cherenkov light, I guess. So Nobel Prize winning effect. So when you have neutrons creating a signal in your TPC, this signal is identical to what dark matter would create. So you can't tell them apart whether it's a neutron event or a dark matter event. But if you can catch those neutrons in the surrounding regions of your main detector, then you can prove that this is the event that just happened is a neutron event, not dark matter event. So this is what this detector does. We have arrays of 8-inch PMTs. They can see Cherenkov light. And if there's a neutron creating a signal in the TPC, and then they come out. So neutrons, they very likely they will be captured in water, in particular captured by hydrogen. They can emit 2.2 MeV gamma. And 2.2 MeV gamma can interact with the water, so they kick out electrons or pair production, producing electron or a positron. So they can create Cherenkov light. So they can be seen by those 8-inch PMTs. So by this event matching, we can reject the possible background nuclear recoil events, right? So, and we also place the PMTs at the bottom and side of this huge tank. The spacing is much larger, so we can detect cosmic rays. As I mentioned, the Jinping lab is very deep. The cosmic ray flux reduction is on the order of 10 to 8. So we don't expect many cosmic rays there, but still, with this 1 kiloton detector, we see some 30 muons per day. It's a shockingly low number already, but we still see muons. Okay, here I'm just showing the recent PandaX result. How to read those plots is the same as before. And it can be converted to limits on the cross-section for different masses of the dark matter particles. As in other experiments, no excess was found, so a limit was drawn here. And so this is from PDG. I guess it's more or less the global picture. So I think PandaX result was in 2024, xenon and LZ. So LZ has a larger fiducial volume mass, so they are quite sensitive. So currently they have the best limit. So those three experiments, they take turns to be the best. But LZ recent result is beating the other two. Okay, right. So if we look at this plot, as I mentioned before, this light blue region, this is what we call neutrino floor or neutrino fog. You can see we're actually getting very close to this edge. This is created by solar boron 8 neutrino. And so instead of treating it as a background, one can look for them. One can measure them as a signal. So I don't know if you heard of the quote from Super K that yesterday's background is today's signal. This is yet another example of treating our background as a signal. So you can do measurement. So left plot is a PandaX measurement in 2024. You can see this little axis, the data points versus the green part. The magenta part is the contribution from boron 8. Of course, when you do this search, you have to assume there's no dark matter, right? It's a bit contradictory that, we assume no dark matter, then we can measure solar neutrinos. So the right plot shows more recent results from LZ or xenon. They can already reach 3 or 4 sigmas. So this was a big hit in the field because we know the neutrino floor should exist, but this is the first time we see it. Even though the flux measurement itself is not as good as, say, SNO or Berkeley. But the significance is that we have reached the tip of neutrino floor. We can see them. That's why PandaX result and the xenon result were quoted as some highlight of the year by the APS. Okay, now coming back to this plot. What should we do next? So you can look at this in two ways. We want to reach the neutrino floor. And we need to increase the target mass. At the same time, we want to reduce the background. I will not discuss too much, but just say that if you increase the mass, but your background level doesn't decrease, then it's not very helpful. I think if you're interested, we can discuss. So you have to reduce the background level at the same time. Otherwise, your sensitivity only increases as I think square root of the exposure. Okay, and the other direction is to go lower threshold, so you can detect WIMP with the smaller masses. Okay, so there are two proposals for the future. One is the so-called XLZD. This is a combination of xenon, LZ, and Darwin experiment, mainly Europe and US. And then there's a Panda-X. So both of them have released their, say, the conceptual design. So the detector is much larger. It can contain tons of xenon. So it's more than twice as large as the current detector. And so I will just say more about the Panda-X exton since I'm more familiar with it. So the plan is use some 40-ton xenon. So this number, since the detector is not there, you can say any number. But this number is more or less judged by how much funding can be obtained. So about 40 ton. I think XLZD, their number is quite high, some 80 ton or so. But I think not much difference, right? Before you're getting this much xenon, whether you claim 80 ton or 40 ton is the same. You don't have it. So Panda-X is a 40 ton. And so the hope is that we can reach the neutrino floor and also have some good sensitivities for neutrinoless double beta decay, as Liang Jian mentioned earlier. So we hope to reach this so-called inverted mass ordering region. From Juno result, I guess, we know the hints of normal ordering. So this is maybe not so convenient for neutrinoless double beta decay search, but still, if we can reach the inverted mass ordering region, we can cover a lot of parameter space, even though it's normal ordering. Okay, so there are two phases. The first step is what we call Panda-X 20 ton. This is actually already in preparation. So all the detector pictures I showed earlier, those are gone. So the detectors have been torn apart, disassembled just maybe 2 months ago. And now we're trying to prepare things for 20 ton. So there are a lot of R&D works in Shanghai. And the hope is that next year we can start collecting data. Okay. Again, so I was talking about neutrons and about neutron veto. So we also have plans for how we better veto neutrons. So in addition to the water Cherenkov detector that I mentioned earlier, we're also considering putting the liquid scintillator really close to liquid xenon. Not only it can provide higher veto efficiency, but also there's a special benefit that maybe they can provide some support to the container of liquid xenon so that we can make this container wall thinner. The less material you use, the better. So anything is radioactive. So if you can use less of them, that's better. So that's the idea. Actually, it's based on multiple ideas in the field. So one special thing about liquid scintillator under minus 100 degrees is that it becomes cloudy. But we hope to get around this by using wavelength shifting fibers to collect light. It's sort of like liquido-like concept. This cloudiness actually helped with the light collection. Okay, so the future layout I put here. You can see this plot shows a summary of how progress has been made over 40 years already So you can y-axis is the cross-section, x-axis is the year number. You can see in the recent years, the best limit is pretty much driven by liquid xenon detectors. Although some liquid argon detectors also has a very good future reach. So then we will eventually hit this neutrino floor. But then the question is, what happens after? If you hit the neutrino floor, do we stop? Do we just so much background, then we give up? The answer is no. There are ways around. So this is the so-called directional detection. So I mentioned earlier that as we are swimming in the dark matter pool, the dark matter actually come to us in a specific direction. So if you look at the sky, they come from the direction of the Cygnus constellation, and so it has very specific direction. If we can do particle tracking, if you can tell which direction it goes, then it can reject background very significantly. You can just look for signals in a very narrow direction, and you worry less about the solar neutrinos because it's coming from different directions, and you worry less about atmospheric neutrinos because now you are selecting only particular directions for those background, and all the other directions that atmospheric neutrino pass, you can ignore. So that's how we can go down to the neutrino floor. Right, so here I give one example. This is, I guess it should be called a proto-collaboration. It's an effort coordinating worldwide this tracking detector effort. So the main technology is the so-called gas TPC. With gas is much less dense compared to liquid. With liquid xenon, you cannot tell the direction because the track is only millimeter size. You don't know the direction, but with the gas, it's much longer. You can tell the directions. So with this, you can build projection chambers. You can see the elements considered here. This I mentioned before. This fluorine, this is actually sensitive to spin-dependent dark matter interaction search. So you can see those modules can be placed anywhere worldwide and forming a big network. Okay, so so far what I have been talking about is direct detection. So this is maybe the biggest category of the game, but that's not all. So if you look at this Feynman diagram-like plot, so dark matter on the left, standard model particle. On the right, we don't know what happens in the middle. But for the direct detection, we have been looking at the scattering of the dark matter particle on the standard model particle. That is, we look in a vertical direction, right? So we look for the recoil here. So that's what we call direct detection. But at the same time, we can look at this diagram in different ways. For example, we can have the standard model particle colliding with each other. They can produce dark matter particles. This is the collider approach. And we can also have signals from dark matter annihilation. So that is to look at this plot from left to right. So dark matter annihilate, produce maybe gammas or other particles. So this is what we call indirect search. So for the indirect search here, I just highlight two anomalies. They can be dark matter or something else. So one is what we call this Fermi-Lat axis. So this is a satellite-based telescope. This large area telescope is part of it. And it can detect gammas in a wide energy range from tens of MeV to a few hundred GeV. And then you can do the survey in the sky, and you can see where our galaxy is. At the center of the galaxy, there seem to be some axes compared to what we can expect for gammas coming from the galaxy center. So we don't know what it is. I think people try different models, and the access is still there. This is a puzzle. And another puzzle is the result from AMS. AMS is also a space-based detector. It's installed at the International Space Station. It has magnets, so you can tell particle from antiparticle by the bending of the tracks. So they can detect positrons, but they see some large access at a few hundred GeV. So this, we don't know the origin of it. So could it be dark matter or something else? So hope this can catch your attention that maybe this is something to work on, right? Okay, and for the collider, I will not mention much. So the main technique is that if you have dark matter production in a collision, then the dark matter you cannot see, right? So there may normally we would expect conservation of momentum, but if you have something you don't see, then the conservation of momentum by visible signals is broken. So then this is one of the main techniques to look for them in the collider experiment. Okay, so I will end with this summary. I've introduced the different detection techniques, 3 different signal types, and we have a search method other than the direct search. So I started this lecture with Vera Rubin. I guess I will also end with it. So much progress has been made. We have been narrowing the parameter space for dark matter. So this, for the future, this requires a synergy from different areas, very different areas. So from cosmic microwave background studies or gravitational lensing. On the particle physics side, direct detection, indirect, and collider searches. I guess either one of them would cost the whole career of a person. So one can only become expert in one of them. Right. So on the astrophysical side, so Vera Rubin Observatory finally started taking data, and so they will do surveys. They will try to measure the dark matter distributions in the universe. So hope is that there will be more knowledge coming from that end. On the particle physics side, as just mentioned, there are next generation experiments that hopefully we can further eliminate possibilities, and if we're lucky, we can see dark matter. Okay, thanks. Yeah.
First of all,
yes.
Like Fermi lot, this signal, it was mistaken calibration.
Oh, a
it's
calibration.
Completely roll out. So
I see.
You can forget about that.
Okay.
And second one, don't forget about pulsars. We always can make like a life for dark matter better.
Yes, pulsars or supernovae, I guess.
Supernova less, microquasars, yes.
Okay.
Thank you very much for your great lecture. I have 2 small questions. The first one, on the slide 68, regarding to the pulse shape discrimination. The ratio of singlet and triplet states depends on ionization density, and if we go to very low energies, energy thresholds like for WIMPs, the total number of photons is extremely small.
Right.
And thus the statistical fluctuations of photons in photon counts at low energies completely ruin the PCT model or efficiency model.
Yes, I would imagine if you have less photons seen, then I guess whether there's a tail or not will become less clear, right? I don't do liquid argon detectors, but this is what I can imagine, that less light, then more difficult to do this sort of identification.
Okay, thank you. And second question is like a general question. You mentioned different types of detectors like CCDs, scintillation detectors. Which detector is, in your own opinion, is the most promising detector for the future for detecting the particles of dark matter?
It depends on the energy WIMP mass you're looking at. So for xenon, they're good at, say, heavy ones. It's tens of GeV, 100 GeV level. Argon, they are more sensitive to, I guess, less, maybe a few GeV or so. And those semiconductor detectors, some of them are good at, say, MEV level dark matter.
What about CCDs?
CCDs, I think, is sub-MEV, right? I mentioned. Wait a second. Right, here. Did I say anything here? MEV level.
Thank you.
Yep. So, I guess they all have their own advantages. I don't want to. It's video recorded. I won't, right.
Yeah, thank you for your presentation. I have a general question about the components of dark matter. It's maybe more for yesterday's presentation, but still, we know that there are models of particles which form the dark matter, and these particles are the same, specific, and they are identical. But are there any discussions or models which assume that dark matter particles are just the particles we haven't found yet, and that they can be different in nature? So I know that it's general, but it will also affect the way we want to detect them.
Well, in general, we don't know what they are. So they're not the particles that we know of, that's for sure. And all the rest we don't know, whether it's a black hole or particle or something else.
I mean, like models assume that they are the same, like exons, primordial black holes and all that. But are there models that can assume that they are different in nature?
Then you have a combination of models. I can only say it's possible that they have different natures. It's not a single thing, that it's a composite matter. And I guess that just makes the problem more complicated. If it's a single thing, that's easy to solve. I'm sure some faint stars, they contribute, right? We don't see them, they have mass. And some rogue planets, maybe some black holes, they contribute. I think we already know some of them should contribute, but the question is whether there's a dominant single explanation for all of those. Yeah.
Thank you for your lecture, Professor. I have a question about the neutrino floor. It's a big problem to all dual-phase liquid xenon TDC. So you said more is different, so we decided to design a 20 tons liquid xenon TDC in X, right? But I think the key is how to distinguish the neutrino from dark matter.
Well, if you look at single event, there's no difference. So that's why they are background. But you try to find ways to narrow down your signal window so that you have less background. So I talked about the directional measurement.
You said that method is named directional it can only distinguish solar neutrino from dark matter, but what about the cosmic high-energy neutrino?
Well, if they are coming from the direction of the dark matter, then it looks the same. There's no difference. But there is one more handle that I think I briefly mentioned, this spin-dependent search. So neutrinos are not so, not so much, wait, let's see, spin-dependent. Right. So this is another way to go for below neutrino floor. So it's very weak. We difficult to set a strong limit. But dark matter can have this spin-dependent interaction. Neutrinos, on the other hand, to my understanding, is not so much sensitive.
Is it possible for us to distinguish them by spin?
By
spin-dependent search.
Spin-dependent search.
Yes.
Yeah, so if the neutrino doesn't create signal, then you essentially eliminate the neutrino background, right?
Okay.
This is one handle, but it's a very weak signal, hard to detect.
Thank you for your lecture, Professor.
Sorry? I think time is very short, really short.
Well, then maybe in person.
Yeah, we can chat afterwards.